This video is a continuation of the fundamental theorem of calculus, and this one we're going to discuss part 2, and we're going to talk about how to use it. Um, but the idea behind part 2 here, if you kind of take a look at the notation and what we're looking at, uh, this tells us a lot about the relationship between the derivative and the integral. So you probably have recognized in even our discussions with antiderivatives that when you see that integral symbol, you are undoing what the derivative does. And so that is the relationship that we know of as an inverse function. And we know that inverse functions or inverse operations undo each other. So that's the relationship that we're seeing here in part 2, that if we take the derivative of an integral function, the derivative and the integral cancel out. Now the important pieces to recognize here is that the lower bound always has to be a constant. Okay, so for this to work like this, the lower bound is a constant, and the upper bound is the variable x. Okay, so this one here, the t in here, this really doesn't hold any value or anything. This we would just call like a placeholder. I mean, you could put like a smiley face there. It doesn't really matter. So this is just using a different variable because the variable in this function is the upper bound that is, well, that's the variable, that's the unknown. So essentially what you're doing with part 2 is the derivative and the integral cancel each other out, and then the variable in the upper bound is what you use inside of the function. So if you have the integral of a function and you derive that, then all you're left with is just the function itself. So let's take a look at a couple of examples here. This is asking us to find the derivative of f of x, and f of x is defined for us as the integral from -2 to x of t squared divided by t squared plus 1. And so what we're doing when we take the derivative of this function is we are deriving the integral. So just like we saw in the definition of the second part of the fundamental theorem of calculus, the derivative and the integral cancel out. And my upper bound variable here, the x, this is going to take the place inside of my function. And so the derivative is x squared over x squared plus 1. And that's how the second part of the fundamental theorem of calculus works in the simplest form. Okay, let's take a look at something that's a little more complex. So this one here, remember the two things I mentioned that are really important to pay attention to is that you have a constant in the lower bound, which we've got a constant there, and in the upper bound we expect to see the variable x. Well, in this case, we have more than just the variable x. So think back to deriving. When we had more than the variable x inside of something, we had to apply the chain rule. And so the same thing is true when we derive an integral where there is more than x in the upper bound. So let's take a look at how we would apply this. We're going to derive the function, and the function here is an integral function. And so the derivative and the integral cancel each other out. That's still true. And the upper bound is still going to take the place inside the function. But because the upper bound is more than x, we also have to derive the upper bound. And so what we end up with here for the derivative is the square root of sine of x times the derivative of sine of x, which is cosine of x. So this is the application of the chain rule in the context of the second derivative, or I'm sorry, the second part of the fundamental theorem of calculus. So we are deriving the integral, which cancels out and replaces the placeholder with the upper bound. But since the upper bound had more than x, we also had to derive the upper bound. Okay, let's take a look at another example that also kind of throws us for a loop. So remember what we're looking for is a constant in the lower bound and the variable x in the upper bound. Well, we can see here that we have the variable x in the upper bound, which is nice, but we do not have a constant in the lower bound. And so what we're going to do for this problem is we're going to apply what we know about integrals, properties of integrals, to create two integrals that we can apply the fundamental theorem of calculus to. Oh, look, I forgot to write this as a function, but our function is f of x here. And so the way that I can do this is I can say that my integral goes from negative x to 0. 0 is really the easiest place to split this, plus the integral from 0 to x. So this is just splitting my bounds at a constant, right? It doesn't matter what constant I use. Like I said, 0 is just the easiest because it separates negatives from positives, and we know that it's different. And so I've split my integral at 0, and now what I can do with this first one here, where I have the variable in the bottom and the constant in the top, is I can flip my bounds. Remember, that's a property of integrals too. So when I flip my bounds, my integral becomes negative. So now I have the negative integral from 0 to negative x of t cubed dt. And then here, this one, I already have the constant in the lower bound and the variable x in the upper bound. So I don't have to do anything to change that. And now my function, I have not changed anything about my function. I've simply split it up so that I have a constant and a variable for the bounds of my integrals. And now I can derive each of these to find the derivative of this function. So I'm going to derive, oops, that should be an x. I'm going to derive the negative integral from 0 to negative x. And then I'm going to derive the integral from 0 to x. Okay, remember that the derivative and the integral cancel each other out. And then I replace the placeholder with the variable in the upper bound. Now this has got a lot of negatives going on here, so let's make sure we keep them all straight. So I've got the negative that's outside the integral. I'm going to plug the negative x in for t into t cubed. And then I have to remember to apply the chain rule, because this is not just an x in the numerator in the upper bound, but it's a negative x. And so I have to derive that negative x. And so I'm going to get another negative 1, right? The derivative of negative x is negative 1. So I've applied the chain rule there because I had more than just an x in the upper bound. The second derivative is much simpler than that. So the derivative and the integral cancel each other out, and I've got just the variable x that's going to get replaced. So this is going to become plus x to the third. So now working all of this out, I've got a negative times a negative times a negative, and that's going to all come out to a negative x to the third plus x to the third. And we can see here that the derivative of this integral is going to come out to 0. Okay, this is because of symmetry. If this kind of freaks you out, it's okay. It's because of symmetry. So the cubic function, just x to the third, looks like this. Remember that area measures, or I'm sorry, that the integral is signed area, right? Signed area. And so from the left side, if we've got negative x and positive x, right, those are our bounds from negative x to positive x, so it's always the negative and the positive side. Your negative area is going to cancel out your positive area every single time. It doesn't matter what that x value is. So that's why this one came out to 0. It just means that the areas, the negative area and the positive area, cancel each other out all the time. Okay. So again, with the second fundamental theorem of calculus, the main idea is that derivatives and integrals cancel each other out. The two caveats to pay attention to is make sure your upper bound is just the variable x, otherwise you have to apply the chain rule, and make sure that if you have variables in both the upper and the lower, that you split your integral so that you can apply the fundamental theorem of calculus in that way. If you need extra practice, my goodness, I didn't even put a page number there. Let me find that real quick. You're going to find this on page number 295. So this is page 295 in the textbook, numbers 75 through 91 odd. Remember, I'm always giving you odd problems because then you can check your answer in the back of the book. And of course, as always, if you have any questions or you need any extra help, please just reach out. Good luck on all this work this week. I look forward to seeing you guys on Friday.